So this video should be the last one of the term. This will be going over some simple hydrocarbons and some information about those. It's kind of a amalgamation of everything that's in chapter 15 in the textbook. It's a little more detailed than what I want to do in chapter 15, so this is going to be just a broader overview. We're going to start with alkanes. We talked about those in our lecture the other day. An alkane is a simple hydrocarbon, so it's just got carbon and hydrogen. So just carbon and hydrogen, and it's all single bonds. We'll get to the double and triple bonds here in a minute. So some properties of alkanes is that they're all very nonpolar, since it's all carbon and hydrogen, and those have relatively equal electronegativities. There's really no polar moments in these molecules, so they're all very nonpolar. So their only intermolecular force, told you intermolecular forces aren't going away. Only intermolecular force is dispersion. Remember, dispersion is prevalent in everything, but it's also very weak, and it's highly dependent on molecular shape. So what we see from only having their only intermolecular force is dispersion is that almost all alkanes or simple hydrocarbons have very low boiling points. So this means they tend to be already in the gas state. So one example is ethane, which is C2H6. So it's a simpler hydrocarbon. It's very low molecular weight. Its boiling point is negative 89 degrees Celsius. So it's almost always going to be in the gas state unless we get down to negative 89 degrees Celsius, then it'll be in the liquid state. Comparably, the same number of carbon atoms, but a alcohol, so ethanol, which is also C2 as ethane, but it also has the OH group on there. Because the OH introduces some hydrogen bonding, its boiling point is 78 degrees Celsius, so much higher, almost 100 degrees difference. So because of the low boiling point, or because of the only thing is dispersion forces, these all have very low boiling points, and they're highly dependent on molecular shape. So remember that the flatter a molecule is, the more dispersion forces it has because of a higher surface area. So if we were to look at pentane, which is C5, looks like that. We can decorate it with all of the hydrogens, but I'll just leave it as it is. So each one of these junctions is a carbon atom, and there are some hydrogens attached to there. So actually, let's just draw these in just for clarity of it. There's 2 on all of these, so that each carbon has 4 bonds, and there's 3 on the ends. Pentane has a normal boiling point of 36.1 degrees Celsius, and that's due to its large flat shape. If we look at an analog or a constitutional isomer of pentane, which would be 2,2-dimethyl propane. So even though it's propane, it only has a 3-carbon chain, it still has 5 carbons, so it's a constitutional isomer of pentane. This looks like it has 1 central carbon atom with 4 other carbons around it. So there's our 5 carbons, and each one of these has 3 hydrogens on it. So still C5H12. Another way of drawing this would just be drawing a stick figure like that. So there's a carbon in the center of this, and we're not drawing the hydrogens around it, but each one of these ends is also a carbon. So same thing. You're going to have to get used to, if you're going on to organic chemistry, you're going to have to get used to this simpler notation, because we do that a lot to save time. No one's going to draw out all the hydrogens. Anyway, because of this smaller, compact, spherical shape, it doesn't have as much surface area. Its boiling point is much lower. It's only 9.5 degrees Celsius. So it doesn't seem like a whole lot. It's less than 20 degrees Celsius change, but in terms of just only changing their dispersion forces, that is a big difference. Next up is alkenes. So it's a hydrocarbon with at least one double bond. And by that I mean one carbon-carbon double bond. They have the generic formula of CnH2n. So remember with our alkanes, those are CnH2n plus 2, so we're taking away 2 hydrogens. Another term for this is we say it's unsaturated. Alkanes are always saturated, and by that we mean that it's completely full of hydrogen. So we say it's full of saturated, or it's saturated with hydrogen atoms. This is, by the way, where we get the term saturated, monounsaturated, polyunsaturated fats when we're talking about different fats. And you'll see that later on in organic chemistry, talking about saturated versus unsaturated. So they have the generic formula CnH2n, and the suffix that we add, so with alkanes, the suffix that we added was ane. The suffix for alkenes is ene. And another important note is that the double bond restricts rotation. So let's look at butene. So that's going to be, the but is 4 carbons. So we're going to write 1 butene. So that means it's 4 carbons. So let's do 1, 2, 3, 4. And we're going to say, so this 1 out front of the name here gives me the position of the double bond, or the ene group. So if we start with the left and we just do 1, 2, 3, 4, just number those like that. This carbon is going to have the double bond, that's where it starts. And then we have our others, the rest is going to be hydrogens. Now this carbon on the left, carbon number 1, only has 2 hydrogens because it has 2 other bonds, so that gives it its 4. And similarly, the central carbon already has 2 bonds, or sorry, carbon number 2 already has 2 bonds to carbon number 1, so it only needs 2 more hydrogens. So there's our 1 butene. We could also draw 2 butene. So again, that's going to be 4 carbons. But now the 2 tells me that the double bond is going to start at the 2 group. So it starts right there at the second carbon. And so again, this would be 1, 2, 3. This one only needs 1 hydrogen. This one only gets 1 hydrogen. And 1, 2, 3. These still have the same number of hydrogens. You can count them up. It should be 2n. So if we have butene, that's 4. This should have 8 hydrogens. And sure enough, they do. Now remember, with a double bond, this geometry should be 120 degrees. They're going to be trigonal planar, or they're sp2 hybridized. So it's not actually what this looks like. What it actually looks like, if we were to draw the correct geometry, is that all of these would be 120 degrees from each other instead of 90 degrees like I've drawn them. So this would be 120 degrees, that would be 120 degrees, this would also be 120 degrees. So it's 120 all the way around. Now, as we said in the second bulletin here, or the last thing, is that a double bond restricts rotation. So if we go back and look at a simple ethane molecule, so this is the alkane version. Is that because this single bond, we only have the sp3 hybrid orbital in the middle overlapping, this bond can rotate about that axis. So if we draw a line through the middle here, it's spinning around that axis. And it can rotate, so these groups are rotating. And that's if we held this other end. In reality, what they're both doing is they're all spinning. But if we look at the ethene, which is the double bonded version of ethane, that double bond is the overlap of an sp2 orbital which has that direct head-on overlap, so it can rotate. However, there's the unhybridized p orbitals forming that double bond, and it can't rotate. If it rotates, it's going to break that double bond, and that's going to take some energy. So these don't rotate. Do not rotate. And that's not entirely true. There is rotation, it's just restricted, and it takes some energy. So what you're going to learn in organic chemistry is that these things get locked in different positions because of that rotation restriction. One of those rotation restrictions leads to something. This is one form of stereoisomers. We call them cis-trans isomers. So with cis-trans isomers, if we look at our butene molecule again, so this would be our 2-butene. What we have here is that these methyl groups are on opposite sides of the double bond axis. And so what we would really write this as is trans 2-butene. So the trans tells us that these are opposite sides. Opposite sides of the double bond axis. So if we were to do our butene molecule again, our 2-butene, but this time we put the methyl groups on the same side of the double bond axis. So there they are on the same side. They're going to be cis-2-butene. And so cis means same side. So if you've ever heard of, and I'm sure you have, if you've heard of trans fatty acids or trans fat, that's what that trans is talking about. It's talking about in that fat molecule there's a double bond, and that way that double bond works is that it is a trans fat. So if we were to look at a long fatty acid chain, it looks something like this. And if we have a trans fatty acid, that means there's a double bond, and these two groups are on opposite sides of the double bond axis. Whereas if we look at a cis fatty acid, the two groups, no matter how the chain looks after the double bond, they are on the same side of the double bond axis. So this is the difference between cis and trans fatty acids. Now, trans fats are so bad because our body doesn't really have a good enzyme to break apart a trans double bond. It takes a lot more energy to break that bond apart, versus the cis double bond is fairly easy for our bodies to break down. So that's why trans fats are so bad for you. Alright, lastly is alkynes. So alkyne is a hydrocarbon with at least one triple bond. So that's a carbon-carbon triple bond. And this has the generic formula. Again, we're taking away another two hydrogens from this molecule. So this is CnH2n minus 2. And we use the suffix of YNE-ine. So this could look like if we wanted to do 1-pentyne, that would be 6 carbons. Or sorry, 5 carbons. And the double bond, or the triple bond, YNE, is going to occur at the number 1 carbon. So this only gets, since this has 3 bonds on one side, it only needs 1 more. The second carbon has 4 bonds already, so we don't add any hydrogens to it. And then we'd add the remaining number of hydrogens we need on the other side. So if this is pentyne, this should be 2n minus 2, so this should be 8 hydrogens, and there are 8 hydrogens, so we're good. We'd say C5H8. In general, alkenes and alkynes, the double and triple bond are electron rich. They have a lot of electrons between them, and so they tend to be reactive. compared with alkanes. Alkanes are relatively unreactive. So this leads to a discussion of functional groups, because we can consider a double and triple bond as part of our functional groups. So functional groups are just specific patterns of bonding in organic chemistry that lead to a lot of really predictable reaction chemistry. So functional groups, no matter what molecule they're in, tend to react in quite the same way. So the first one is, just as we talked about, is the alkene and the alkyne. Another one that we've encountered a lot in lab and lecture is alcohols. Something else we haven't talked about too much, but they'll come back a lot, is halogens. So when X is a halogen, that could be fluorine, chlorine, bromine, or iodine. This is called a haloalkane or a haloalkane. Another one that we see a lot of is a carbon with a nitrogen. These are called amines. So amino acids carry this, there I wrote amino. An amine has an amino acid has an amine group in it. Another common one is the amide group, which is a double bonded carbon with oxygen with a nitrogen on it. So peptide bonds tend to be amide bonds. This might look familiar to the biochemist. This is a peptide bond. It's an amide bond. Another ones we encounter a lot are aldehydes and ketones. Between two carbons. So a double bonded carbon-oxygen bond between two carbons is a ketone. Aldehydes and ketones are fairly volatile. They have high vapor pressures and low boiling points, so they tend to be gases. So this is responsible for a lot of the odors and flavors in the food we eat. And carboxylic acids tend to be, because of the hydrogen bonding, tend to be a little less volatile, but they also are parts of our food chemistry. So these are really prevalent in a lot of our foods that we eat. That's a carboxylic acid. And we've seen that in acetic acid. Similarly, esters are relatively volatile. So that's a carbon double bonded with an oxygen with another oxygen between another carbon. So that's an ester group, and these tend to be responsible for a lot of flavors as well, and smells. And a carbon bonded with an oxygen with another carbon, this is an example of ether. So ethers are relatively volatile. They don't have a lot of intermolecular forces. They tend to be in the gas phase a lot, and these are responsible for a lot of gases, like diethyl ether is one that's used as an early anesthetic, so it's really easy to inhale and knocks you out. And then one last group, you've probably heard of this one a lot. This is the gloves that we wear in class. This is a nitrile group. So those are nitrile gloves, are a polymer of this group. And that's really the more important functional groups. There is a lot more than this, but we're really just going to focus on these. And even more specifically, the ones you're going to encounter in organic chemistry a lot are the ones I'm drawing with an orange star next to them. These ones tend to have a lot of the predictive chemistry that we can talk about. Amines and amides, we talk about those as well. But these kind of 7 core groups are really predictive in terms of their chemistry. We can readily oxidize and reduce these into their various forms as we go through and learn organic chemistry and reactions. But this is really all I wanted you to know from organic chemistry at this point, and we'll carry on with this when we get to organic chemistry next year.